Okay, so this is a big review problem. So we're going to factor. So at the top we got, how does the bottom factor?
X plus 7.
7 minus 2. Okay, this is a situation where you have to be able to factor it, you guys, because the only way that wholes appear are if you can cancel. Wholes come from canceling. So I have two identical parentheses. Gang, close doesn't count. They have to be exactly the same. Wherever the factor is that cancel, that's what the x coordinate of your whole. So the fact that I canceled out x plus 7 means I'm going to have a whole where x is negative 7. So the x coordinate comes directly from the factor that I canceled out. The y coordinate is found, like y's are always found, by plugging in the x. That's how we get y. We plug in x. So if we plug in negative 7 for the x's in this problem, don't try to plug it in over here because it won't work. You do 0 in the bottom. You got to plug it in the new problem. So that, what is that, negative 14 over negative 9? So that should be 14/9. Now you can look at what's left here, and you can see that you have a vertical asymptote at x equals 2, because that's what makes the denominator 0. That's a cannot be. And then we have a horizontal asymptote. That's, you box it in. That's how you find your horizontals. You box it in. You can do it in the original, or you can do it here. It isn't going to matter. You're either going to have x squared over x squared, which is 1, or you're going to have x over x, which is also 1. Your horizontal asymptote is a 1. Now, I warned you, and I'm starting to take off points. When you write your asymptotes, they are equations. If you just put a number, you're missing half credit. It's x equals for the verticals and y equals for the horizontals. And then the whole is an actual ordered pair of points. All right, does that clear that up?
Yeah.
All right, anything else from the quizzes? Read.
So on the next question on the quiz, you said find the domain.
Okay, what was the equation?
Square root 5x plus 15 over x plus 1.
Square root 5x plus 15 over x plus 1.
Mm-hmm. So like when you're doing like 5x is greater than negative 15, and then you get x is greater than negative 3. Do you not flip it to a positive 3?
No. Whatever is under the radical has to be positive. So you're going to say 5x plus 15 is greater than or equal to 0. So then you just solve it like regular. There's nothing weird that you do. You just solve that inequality. So x has to be bigger than or equal to negative 3. But x can't be negative 1. So your domain is everything from negative 3 to negative 1. So that would be negative 3, negative 1. Or everything from negative 1 on. And we're big kids now. We're writing our domains as intervals. Some of you got real lax on your homework. Make sure you're writing your domains and your ranges as intervals. All right? Now, I didn't grade carefully every homework problem, so I did make some corrections, like if they were stuck out at me as I was looking through your paper, but I will be posting the answers. You probably want to go back and compare your work with the answers so that you're sure you got it, okay? All right, okay, so now let's look at, I want to see if I have anything to finish up from my notes. Yes, I would like to do a little bit of notes, and then we're going to do one of these review sheets, okay? So we are back in our notes, pages aren't numbered, but it's where we left off, so it's 1.3, number 2, that is referencing the book problems, which you don't need to get your book out. I've taken up enough time here. I'll just get mine out. We're ready for number 22, I think. So get out your BFF sheet. Let it help you. Because we're going to answer some questions about some characteristics of our various functions. So, number 22 says, name 3 functions, so there are 3 of them, and they have infinitely many extrema. Now, what do we mean by extrema? We've talked about that word before. What do we mean? Maximums and minimums. That's right. Maximums and minimums. So look at all of your BFFs. And 2 of them are really easy. Two of the curves that have infinitely many high points and low points are easy. Josh?
Never mind.
Absolute value? No. Here's the deal. Let's make sure we understand what it means to be a maximum or a minimum. When I graph my absolute value function, it definitely has a minimum. That is both a local minimum and an absolute minimum. It is the low point on this graph. But the problem says I want to have infinitely many of those. Infinitely many of those would mean lots and lots of low points and or high points. Roy? Linear. Actually, the linear has no critical value, no extrema, because a critical value, an extrema, is a high point or a low point on the graph. That happens with hills and valleys. Okay? I absolutely know this goes on infinitely, but that's not an extrema. An extrema is something like this. It is a valley or a hill. You gonna try, Josh?
Yeah. Cosine and sine.
Absolutely. Sine and cosine have infinitely many hills and valleys, because what is the shape, guys? I mean, it just goes on forever and ever. Now, it doesn't, the sine and cosine, Rory, don't grow infinitely like this does. This goes forever and ever, but that's not the question. When we talk about extrema, we're talking about tops and bottoms, okay? Now, the other one, anybody want to take a guess what the other one is? Josh?
The logistic function.
No, because the logistic function actually, it's bounded, but it doesn't have a hill or a valley. It doesn't have any critical values or any extrema. It's my least favorite function, the greatest integer function, and here's why. If you look at the greatest integer function, if you look at this locality right here, this spot right here, that's as high as the curve gets. That would be the maximum value right here. But what about this piece? That is the maximum value for this locality, and then another one, and another one. I don't like the absolute value, or I mean the greatest integer function, because it's all the weird things happen with that one. Those are considered local maximums. So they are technically extrema, and therefore there are infinitely many of them because it goes forever. Okay? Now, on a test or quiz, I'm not going to say name them all. But I might say name one that has infinitely many. And usually you can find one. It's just when you throw in these weird ones. All right, what's the next one? 3 functions with no zeros. Okay? So there's 3 again. and they have no zeros. This is number 23. No zeros. What do we mean by zeros? Where we cross the x-axis. So if we have no zeros, then we are looking for 3 curves that do not cross the x-axis. Can you find 3 of them? This is a lot easier problem. Annie?
The
Logistic, absolutely. The logistic does not cross the x-axis because doesn't it have an asymptote there? And another one here, and it squiggles in between, so it does not cross the x-axis. Good. Liz? Exponential does not cross the x-axis. Again, doesn't it have, think about what that looks like, guys. Look at your sheet there. Doesn't it have an asymptote here? So it's not crossing the x-axis. One more, Grace. Reciprocal. Very good. Reciprocal. And you can abbreviate if you want to. The only one, I think I mentioned this yesterday, you can abbreviate is this one. Don't abbreviate that one because it gets confusing with the logarithm. Okay, good. That was easy. All right, again, this is number 24. Now we want 3 functions that have a range of all real numbers. So the range, the range is negative infinity to positive infinity. Now I want you to stop and think about that for a second. That means that the curve goes all the way down, Rory, all the way down with an arrow on the end, all the way up with an arrow on the end, and no breaks in the middle. So can you find 3 curves that do that? All the way down, all the way up, no breaks in the middle. That's what that means, right there. Read, give me one. Cubing function, absolutely. The cubing function, all the way down, all the way up. What else? Caroline?
linear.
Linear, yep. Absolutely, one more, Jacob.
The natural logarithm.
Yep, the logarithmic function, very good. Remember, the logarithm has an asymptote here, but it goes like this. So all the way down, all the way up, and no breaks in it. No vertical breaks in it. Okay, that's pretty easy. All right, let's see, how far did I go? 25. The 4 functions, okay, we need to talk about this. The 4 functions that do not have this behavior. So end behavior is not, let me try to get it right here. Okay. Whoa. Did we talk about this the other day? End behavior? It looks so scary, but it's very, very easy. This says, now remember, we're looking for ones that this is not. But this says, as you go to the right, this tells you what X is doing. X is going to the right. So think about your picture. As you go to the right, you're also going up. Remember, f of x is y. So this says x is going right, positive, and y is also going positive. So I'll just draw one. The linear function, isn't that the behavior you see right here? As you go right, you go up. So that would be an example of one that does this. I want you to find 4 that don't do that. So can you find 4 functions that as they go right, they are not going up? Can you find 4 functions, or they're not heading toward infinity. I mean, they're not infinitely shooting off into space. As they go right, they are not shooting off into space. Jacob?
I was going to say the logistic function.
You are exactly right, Jacob. You are exactly right. Because what does the logistic function do? As it goes right, it is going up. Agreed?
Yeah.
But it's capped at 1. So is it heading to infinity? Is it shooting up into space like this one is? No. So that is exactly one of them. That's right. What else, Josh?
Sine and cosine.
Sine and cosine, absolutely. What do sine and cosine do? They just go up and down, up and down, up and down. They do not shoot off into infinity. They go on forever and ever, but they're not shooting up into infinity. Great. All right, can you think of another one? There's only one more, I guess. Jacob?
It's the greatest integer function.
No, because think about what that looks like. As you are going to the right, as you're going to the right with the curve, do you keep climbing forever and ever without, I mean, there's no cap on it, right? It just,
focused on the line.
yeah, no, it keeps going forever and ever. Read?
Square root.
No, think about what the square root looks like. As you go to the right, that is still going up, 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 up forever and ever. There's no, like, nothing stopping it. So this says there's nothing stopping it. It just keeps getting bigger the farther you go. Oh, you know, we've already talked about it today.
The reciprocal?
The reciprocal function. Because what happens in the reciprocal function is, as you go to the right, so I'm not looking at that side, as you go to the right, what is your curve getting close to? 0, the axis. It isn't shooting up into space, right? This says as you go right, you go up. That does not do that. Josh?
What's the equation for the reciprocal?
The reciprocal function is y equals 1 over x, and the logistic function is 1 over 1 plus e to the negative x. That should be on your paper. Why is that not on your paper? I don't know either.
I have everything else.
Okay, gotta have it all. All right, there's 3 more, and then we'll do a little bit of review. All right, so there are 3 functions. I'm looking for 3 now. These problems are straight out of your book. I'm looking for 3 of them that have end behavior. They have it. Their end behavior is, as we approach negative infinity, we're going to negative infinity. Make sure I copied that right. Yep. So what that means is, in like regular talk, not math talk, but regular talk, as I go left, I am going, that's a negative there. As I go left, I am going down forever. No stopping. So can you think of 3 functions that do that? As you go left, you go down forever and ever and ever. Linear, absolutely. It shoots down like that. Cubing. Linear and cubing have many of the same features, don't they? There's one more. As you go to the left, you're going down forever and ever. Okay, let's look at the reciprocal function. Remember, we're talking about going to the left. So as I go to the left, what is my curve doing? Is it going down? It's actually going up towards 0. Greatest integer, absolutely the greatest integer. Because when you graph the greatest integer, when you graph that, don't you just keep going down, guys? Yeah, there's nothing stopping it. You're just heading down, 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 down. Okay. right. So now let's see two more. The four functions whose graphs look the same when turned upside down and flipped about the y-axis. Okay, so there are four that look the same when I flip them upside down and across y. All right, this takes some visualization. Look at each of your pictures. Imagine flipping it upside down and then across y. So this way. So you're going to flip it upside down and across y. Ollie?
Reciprocal function.
Reciprocal function. I don't know. Let's check it and see. If I take my reciprocal function and flip it upside down, it's going to look like that. And then when I flip it across y, it's going to look like that. Oh, I think he's right. I think that's one of them. Anybody want to take another guess? I was thinking linear for some reason. Here's the linear equation. If I flip it upside down, it looks like this. And then if I fold it across y, doesn't it come back to the original?
So then is it cubing?
That would be a very logical guess. Let's check it real quick. Here's the original cubing. So upside down would be this. Flipping it across y would be the original. Yep, perfect. Is there another one? Logistic? I think that's going to be a problem because when I flip it upside down, it's actually going to be down here now. And then when I flip it across y, it's still going to be down there. It isn't going to come up.
What about the absolute value?
I think that one's going to have the same issue because if I flip it upside down, I get this. And then if I flip it across y, I still have that, but I need the v up there. So I really need something that's in the top and the bottom. Josh? Greatest integer. Alright, so let's look at that for a minute. I'll just graph that much of it. Okay, now if I flip it upside down, that one's going to stay put, and this one's going to come down here, and this one's going to come up here. Okay, I'm going to get rid of that now. Those are the originals. Now when I flip that across y, it's going to look like this. That's a tricky one, Josh, but you know what? That isn't the same thing because the dots are in the wrong spot. So it's a great guess, but I don't think it's the same. What would it be?
Natural logarithm function?
Logarithm?
Yeah.
All right, let's look at the logarithm. I really don't know what the fourth one is. I'm trying to think of it. Let's see. Does logarithm work? So here's the original. When I flip it upside down, it's going to look like this. So this is the upside down. But when I flip it the other way, it's going to be over there and not over here. So, shoot.
What about like sine and cosine?
Oh. Let's look at sine. That's the original, right? If I tip it upside down, okay, so I'm going to erase that. That's the original. If I tip it upside down, that's what I get. If I flip it across y, that means this bump comes over here, and this bump comes over here. That's it.
Okay, but then why wouldn't cosine?
All right, let's look at cosine. So cosine starts out looking like this, right? So when I turn it upside down, I get the blue, so I'm going to take out the black now. That's the upside down. And then when I fold that across the y-axis, does that change? When I fold it across the y-axis, doesn't it just stay right where it is? So no, it doesn't do it. Okay, see how we figured that out though? We just tested them. All right, there's one more. This is easy. The two functions that are identical except for a horizontal shift. They're exactly the same picture, but one is just shifted over from the other one. Sine and cosine. Look at your pictures for sine and cosine, you guys. Aren't they exactly the same? Except the hills and valleys are shifted? Yeah, they're identical to each other, except the hills and valleys are shifted. Okay, good work on that. Next, we're going to do a little bit on our calculator and do some piecewise functions. Before we do that, though, I want to do a little bit of catch-up because our next class, which for you people is what, Tuesday? Right? We have class tomorrow?
Yeah.
Yes. Okay, good. Okay. So I can't do it tomorrow, though. So we'll do it. I don't know. I'll let you know when we're going to do it. Whenever our next class is after tomorrow, we're going to have a quiz. So we're going to do a little review. And then tomorrow we'll do a practice quiz. Today we're just going to do some review problems. Tomorrow we'll do a practice quiz. And then or maybe on Monday we'll do a practice quiz during our Mission Monday deal. And then the day after that, we'll have an actual quiz. Okay, whenever it is. All right, so get out this sheet that I gave you that is called Precal A 1.1 to 1.2 review. Hayden, I just created this thing, so I don't remember. I know I scanned it. I don't remember if I posted it or not. I didn't. So I'm going to open it for you and screen share it. It'll be posted later. Okay?
All right, thank you.
Can you see it? All right. Okay. So, first thing up there at the top, I've been looking through my book and trying to make sure that I've hit everything that's important. And one of the things, a couple of the problems in the book involve factoring cubes. And even though that really doesn't have anything to do with what we're doing right now, it's a skill. I mean, they just incorporated it into a couple of problems. So I want to make sure we review how to factor cubes. You did this last year. Does the word soap ring any bells? Same, opposite, always positive. That's kind of the acronym we remember when we're factoring cubes. So, do you remember how that works? You got a small parentheses and a bigger parentheses. What's the cube root of 8? 2. What's the cube root of 27y cubed? 3y. So my first parentheses is going to be 2 minus 3y. I'm thinking of soap. That gives me my signs. So the first sign is the same as the original problem. Then you remember how to fill in these. You use these. These are the guidelines to fill in here. What do? We square the first one. Very good, Ollie. So that would be 4. Then we multiply these together, and that would be 6y. Remember, soap is giving us the signs, so don't put any signs in. We multiply them together and get 6y, and then we square that one and get 9y squared. And then our signs are same, opposite always positive. Okay, so every difference or sum of cubes, doesn't matter if that's a minus or a plus, every sum or difference of cubes is going to be factored that way. So it's the cube root of the first, cube root of the second, and then you square, multiply, square, and then soap the signs.
Is that as far as you have to go for when just is factored?
That's all that factors. Are you thinking maybe you could factor this?
No, I was just like, I don't know if we had to like.
No, it just says factor. So those are the factors. If we were solving it, like if it were equal to 0, then we would take both of these and set them equal to 0. This does not factor though. That trinomial won't factor, so you would have to use the quadratic formula on it if you were going to solve it. But we're not. We're just factoring. You could solve it, but we're just factoring. All right. Consider the data in the table. Write the equation that best represents it. All right. What do I need to do? I need to get out my calculator. Right? And I need to go to Stat, Edit, and then I need to put in my X's, which are 1, 2, 3, 4, 5. Now, you can't have any additional numbers in there, guys. So either you're going to clear your list or you're going to erase the extras. You can type right over, but if there's any extras in there, you got to get rid of them. I always feel safer when I clear lists, so I'm going to do that. All right. Now I'll type it in. And my Y's are 4, 15, 40, 49, and 72. Now, we're going to stat plot it, right? But before we do that, make sure your window accommodates your X's. So I'm using 0 to 6 for my X's and 0 to 75 for my Y's. Then you got to turn your plot on and hit graph. Now, the graph is not the answer. Why are we doing that? So that we can figure out whether our equation is going to be a line equation or a parabola equation, right? That's the only reason we do it. If you have forgotten how to do this, you either need to go back and do the review, or you need to get in here outside of class time, and I will go through it with you one more time. Okay? Now, what do you think? Those of you that got a plot, do you think that's linear, or do you see some curvature there? There's some curve there. So the regression I'm going to choose, I'm going to go back to Stat. I'm going to go over to Calc now, and then go down to quadratic regression. And the nice thing about your calculators, they set the equation up for you. They say, this is what your equation is going to look like. And your A is going to be 2, and your B is going to be 5, and your C is -3. Right? So that's the equation right there. That's the equation. Now, remember, as long as that plot is on, you're probably going to have issues graphing other things. So when I've done this, I usually just turn my stat plot off. You don't have to, you can leave it on. But when something doesn't graph later on, check that, because that's probably the reason it doesn't. All right, second part of the question says, how many calories will you burn if you work on math for 8 minutes? So look at your ordered pairs. Obviously, you're going to put 8 in somewhere. Is 8 going to go in for the x, or is 8 going to go in for the y? X. So we're just going to plug in 8. So let's see, it's 128 and 37. Did you get 165 calories? Easy, right? All right, consider this function. All right, we haven't done all of this yet, so let's make sure we do. Zeros, we know what to do. You're going to factor this, or excuse me, graph this on your calculator. So let's graph it. Remember, your plot might be on and your window is all screwed up, right? So I'm going to go back and make sure my window is standard. So I'm going to zoom 6. I'm just going to start with a standard window. I'm going to take out all these equations that I have in there right now. And I'm going to graph 4x to the third minus 7x minus 9. And on my standard screen, I see something that looks like this. Does yours look kind of like that? So the first question says, find the zeros. Well, there's only one, and it's right there, right? We know how to find that. We second calc 0. And then we have to have our bound set somewhere over here. And somewhere over there. And then in between. What did you get? Let's round it 1,000. 1.744. So that definitely is old news. We've practiced that. Now, when I look at this picture though, this part's actually off my screen, but I know it goes down and turns round, right? Would you agree that there is a maximum here and a minimum somewhere down here? So I can actually see the maximum set up the way I have it. So I'm going to find that one first. I'm going to find this point right here. Guess what? You do exactly what you just did. But when you go to second calc, you're going to choose maximum. And you're going to set your cursor over here somewhere. And then over here somewhere. And you're going to find your maximum. What did you get for your maximum point? .764. If I rounded 1,000, comma, negative 5.436. Does that look about right? So that's your maximum. So it says, what is the relative, local, 2 words mean the same thing, maximum, right there. That's it, right there, that's your point. Now, do you understand why the word relative or local is there? Where's the absolute maximum to this problem? There isn't one, right? So, this is a relative maximum. It's a high point in this locality. Now, that low point is a little bit problematic because you don't see it, but you can still handle it, kids. You can change your window if you want, make Y go down farther. You can see it. But if you set your, you know it's down there. If you set your left bound over here and your right bound over here and move your cursor down there somewhere and hit enter, it will give you the minimum. You don't physically have to see it, but if it makes you feel better, just adjust your Y min. make y min down farther, and you'll be able to see it. So second calc, minimum now, minimum. And what did you get for your minimum? 0.764, yep, comma, negative 12.564. Everybody okay with that? So the nice thing about minimums and maximums and zeros and points of intersection, it's all the same, right? Second calc, just pick the one you want. Okay, find the domain. All right, we just talked about this. What's our domain in this problem? What do I have to think about? I'm sorry, Caden. Is that better? So what's the domain? Well, x can't be 1, right? And x has to be greater than or equal to 2. So on the number line, what that would look like is, wait a minute. Greater than or equal to 2 would be right here, right? And 1's back here. Is 1 even, I'm not even thinking about 1 if I have to be bigger than 2, right? So my domain is 2 to infinity.
How come you don't put 1 and 2? Like 1 and 2?
Because it has to be bigger than 2. Is that bigger than 2? Are those numbers bigger than 2? That's why. You have to be bigger than 2. If you're not bigger than 2, this numerator will be imaginary. And it can't be imaginary. What about b? What's the domain for b? All reals. And we'll say that's from negative infinity to infinity using our interval notation.
When it's all reals, do you have to use interval, or can you just say all reals?
Well, you can say all reals, that means the same thing. We're trying to get into calculus mode where everything is done in intervals. All right, 5. We've already talked about this today too, but that's all right. We need all the asymptotes and poles. So, here we go. How do we start? Oh my gosh, you're kidding. Shoot. Well, we'll finish that tomorrow. We still haven't finished 1-3. All right, so we'll finish that tomorrow. Thank goodness I see you tomorrow.